Hello class, this is CSE-5250, sections 2 and 60, week 5, spring 2025. Okay, so here is where things start to get interesting. So far in the past few assignments, we have been getting familiar with Pthreads, writing a simple program from the ground up to get it to work, but also to bug fix any issues that come up, mainly race conditions and race conditions and enforcing mutual exclusion so that we get the same result every time without losing any data in the process. Because in our case, the race condition that we previously had encountered in assignment 1 was resulting in some data loss. Assignment 2 had us try to fix it with a busy wait, and that was there to show you how bad it was for our program here. So we instead use a mutex to enforce mutual exclusion. So there is a critical section in the form of adding terms to a global sum. We acquire a lock before we execute the critical section's code, then release the lock once we have left the critical section. There was also one more bug that we had to fix, and that was the fact that this program can only work if the number of threads perfectly divides the number of terms. So we had to bug fix that by adding a little extra code. This is just one way to fix it. So if this is the last thread, have my last I be n, because if the thread count does not perfectly divide the term count, we're going to have some missing terms. So this fixes it up. There was an alternative way of doing this. It works the same, it produces the same result, but just takes a different way to get there. And I think I can demonstrate that right now. So if you imagine a 14 loop, if you imagine a for loop that undergoes 14 loop iterations and we have 4 threads, we have one thread start at one position, another thread start the position after that, thread 3 starts after thread 2, thread 4 starts after thread 3, and they leapfrog over one another. So they increment, so that I++ that you see at the end of a for loop, that I++ that you see as part of a for loop, we replace that with, in this case, this would be I plus equals 4, so we increment by 4 each time. That's how we get this leapfrog. It's also called a stride. So, stride. So the goal is to get each thread to start at different positions and have them take a stride that is the number of threads available. So that way they leapfrog over one another so that any one thread, so that each thread does the same portion of, does roughly the same amount of work, but overall they do all the work together without having to accidentally doing the same work that another thread has done. So this is if we use a stride. The other one was if we divided this by this 14 for loop iterations by 4. So that would be where, so if we instead did it the way that was done in the mutex, where we calculate a first I and a last I, then we would have each thread be assigned 3 for loop iterations each, but the fourth one would be assigned the remainder. These would be the terms that would otherwise be lost if we did not add this code here. So these two methods of dividing the work, either using a stride or calculating a first and last I, they both produce the same results. They just divide up the work in different ways. Okay, so it is the mutex.c code and more specifically the mutex program that we want to run are benchmarking with, because it will have all the bugs resolved at that point. Okay, so let's see what we have to do. So your benchmarking project consists of 4 parts. Parts starting with the part 0. Part 0 is probably the easiest of all. Just see how many CPU cores are on your system. So on an Ubuntu system like this might also be true for other distros as well. You want to look for system monitor. Click that, and you want to go to resources, and right there, this shows 4 CPUs. They're all right about idle. This is how many CPUs we have. We have 4 of them. So 1, 2, 3, 4. If you are on a Mac, you'll want to go to Apple menu, About This Mac, System Report, Hardware Overview, and look for total number of cores. This might vary between different versions as well, so just be aware of that as well. So that is for a Mac. If we could do this on a Windows machine, it's pretty simple. Just open up Task Manager and go to the CPU, change the graph mode to logical processors, and I have an 8-core 16-thread CPU, so it's showing up as 16 logical processors. If you know the exact CPU your system has, and you are running this on a Mac or a Linux distro, you can just look up the CPU and look for the thread count on your CPU. In my case, this is a Ryzen 7 5800X, so I would just look that up. Yeah, Ryzen 7 5800X specs, general specifications, 8 cores, 16 threads. We want the thread count. So, yeah, if you know the exact CPU, you can just figure out what the thread count is just by looking it up. However, if you are running this on a virtual machine like I am, then that's not going to be reliable, because your host is donating some of its resources to your virtual machine or the guest. So what we want is to see how many resources are being offered from the host. So to find that out, you would click Settings here, and you'd get a window for your virtual machine. You want the one for the virtual machine you're going to be running this on. So click Settings, go to System, and click Processor. Right now it is 4 CPU cores. I cannot change that right now because it's currently running, but yeah, 4 CPU cores is what the virtual machine has, which matches up with the 4 CPU cores that's showing up in this monitor here. Okay, so keep a note of that, because we're gonna see whether our own hardware has limitations. So, with that in mind, let's start the benchmarking. Alright, so you are gonna have 2 tables to fill out and several questions to answer. Okay, so I would like you to create a table consisting of the following columns and rows. So for the columns are going to be thread counts. So we're going to benchmark our program with 1, 2, 4, 8, and 16 threads. And we're going to benchmark with different numbers of terms. 1 million, 10 million, 100 million, and 1 billion. We could go finer, but I would rather we do this on an exponential scale, so I guess maybe it's a log scale. So we're just increasing the number of threads and terms by multiplying by 2 and 10 each time. So 1 thread, 2 threads, 4 threads, 8 threads, 16 threads. We can go finer and go linearly, so like 1, 2, 3, 4, 5, 6, 7, 8 threads, but that takes a little bit longer, so I'd rather we just do it like this instead. So doubling the number of threads each time. Similarly with the number of terms, we could go finer and go like 1 million, 2 million, 5 million. And that could work too. Again, this is just so we don't have to do so much work. Okay, so what we're gonna do is we're gonna benchmark our program. So we're gonna start with running our program with 1 thread and 1 million terms. So I'll close this, open terminal, and now we can run our program. So you will need to have finished up Pthreads assignment 2 before you can even begin with benchmarking. So if you haven't finished that up, keep in mind that the late policy for the past few assignments is such that if you submit your work late and it's within 1 week of the original due date, I'll still take it without penalty. But when it comes to the projects, the grace period is only 2 days, and after that, the assignment closes. That's because these are much more important, and I want to make sure everything is on time for proper grading. If something still happens along the way, such as you lost power because it was raining outside, and it was raining outside the other day too. If you have issues with that and you couldn't keep up, just let me know beforehand so I don't unfairly dock you points for a missing assignment, okay? And if you still need to submit after the fact, again, just let me know so I can accommodate you just in case, okay? So for the past 3 assignments, if your assignment was submitted within 1 week of the original due date, I'll still take it. If you submit the benchmarking project late and it's within 2 days, I'll still take it. But if it's after that, I'm gonna need you to come up to me and tell me what happened. So that way, at least that way I know what's going on, and I can still let you get points on the assignment. Okay? Okay. All right. So let's begin benchmarking. So we're gonna begin by typing in / the name of our program is called mutex. So I'll just say mutex. I'm gonna run it with 1 thread, and I'm gonna run it with 1 million terms. Enter. So now we have 1 thread adding 1 million terms, and we get an estimated value of pi to be 3.141592. Perfect. But we're not getting a runtime though. For us to do that, we need to add in time. So time /mutex 1 million. Now we get a runtime of about 5 seconds. For best results, run this program, say 5 times, but the more the merrier. Run it 5 times and get the average runtime. So 5, 5, 4, 4, 4. Take the average of that. So that is 5, 5, 4, 4, 4. So that is in milliseconds. So let's just type that in to a calculator and okay, so 5 plus 5 plus 4 plus 4 plus 4 equals divided by 5. We got a runtime of 4.4 milliseconds. So I can just write this in the table as 0.0044. Whatever units you use for your table, be consistent with it. So say that it's seconds or say that it's milliseconds, and stick with it throughout the table. So I can either write it as this, or I can alternatively write it as 4.4 ms. ms is the abbreviation for milliseconds. Microseconds uses the Greek letter mu. So ms is for milliseconds, mu-s is for microseconds. We're dealing with times on the order of milliseconds here. Okay, so we got an average runtime for 1 million terms and 1 thread. Clear, and yeah, type in clear to clear all that. If you can automate this, more power to you. In the past, I would teach this on a Windows machine, and I would go so far as to tell you how to write a batch script so that you could just automate the whole thing. Unfortunately, my Linux knowledge is not as great as that on a Windows machine. So if you know how to automate it, more power to you. I won't stop you if you automate it. In fact, I would actually encourage you to if you can. Okay, so we're gonna run our program again with 1 thread and 10 million terms. We'll run it 5 times, add up the average run times so that we can get an average. Again, these are all in milliseconds so far, so 29 plus 30 plus 30 plus 30 plus 30 equals that. Divide by 5, that is 29.8 milliseconds. If you know how to work with Excel, you can also just write the whole table in Excel. Because if you do, there are ways to automatically generate the whole table. But that's going to be for part 2 here. When we calculate the speed up, you're going to be dividing times with other times. So, for our next step, we're going to be doing 100 million terms and 1 thread. So, clear 100 million and 1 thread. So, notice that the program is now slowing down. That's because there's just more work to do. So, I'm going to take the time in milliseconds, and that is 284 plus 282 plus 279 plus 278 plus 285. Divide by 5, that is 281.6 milliseconds. So I'll put that in the table. There we go. Finally, we're going to do this once more with 1 billion terms. So I'll type in clear and 1 billion terms. That took nearly 3 seconds. So I'll run it. Run. Okay, so now we have, let me clear this, 2,798 plus 2767 plus 2775 plus 2763 plus 2748. Divide by 5. 2,770.2. So we are getting a proportional increase the more terms we are adding. So with 1 million terms, it was like 4 milliseconds. With 1 billion terms, it's nearly 3 seconds. So you would repeat this process for 2, 4, 8, and 16 threads. What I'm going to do is I'm going to complete 1 row and 1 column just for demonstration purposes. So once you've gotten all the columns in here, we're going to then calculate how much faster it ran. So we are benchmarking against ourselves here. We're not going to benchmark against others here. But we are going to benchmark against ourselves for one particular number of terms. So for us to demonstrate whether we got a speed up at all, we need to complete a row here. So I'm going to repeat the first experiment with, I'm going to repeat the 1 million term case with 2, 4, 8, and 16 threads. So 2 threads and 1 million terms. There we go. We got 5 milliseconds, but I want to get an average 5, 5, 3, 4, 5. So I got a runtime of 4.4 milliseconds. I'm gonna run it again with 4 threads. So now we have 5, 5, 3, 3, 3. Let me just add that up. .8. I'll do it again with 8 threads. Okay, so 1, 2, 3, 4, 5. Let's get those runtimes. 4, 4, 3, 3, 3. So divide by 5. We got 3.4. And we're going to do it once more with 16 threads. Five, 6, 3, 3, 4. Maybe I need to do this again. So 6, 7, 7, 3, 4. 6, 7, 7, 3, 4. So I got a run time of 5.4 milliseconds. So now we have one row calculated on our example table here. We're gonna calculate the speed up for each increasing thread count. So we're gonna calculate how much faster the 2 thread case was compared to the 1 thread case. So we're gonna divide the time for the 1 thread case by that of the 2 thread case. So 4.4 milliseconds divided by 4.4 milliseconds. The units cancel out, but 4.4 divided by 4.4 is the same number, so it's a 1 times speed increase. For here, we have 4.4 divided by 3.8. Let me get the calculator. Let's just call it a 1.16 times increase. And then again, we're going to do 4.4 divided by 3.4. So that's 1.29. And now 4.4 divided by 5.4. So I'm going to put in 0.81. So yeah, we have, for our 1 million term case with increasing thread counts, with 2 threads, we did not get a speed up at all. But again, we might be able to see better results if we ran it for like, say, 10 times each, and then took the average. I'm just saying 5 times because, well, that's a good starting point. But again, the more data points, the better. So 1.1, so 1 times speed up, 1 times speed up. We got a little bit of a speed up once we get to 4 threads, and a little bit more at 8 threads. But once you got to 16 threads, it started to slow down, and at that point we have a slowdown at that point. And at that point we have more threads than there are CPU cores. So each CPU core can run 1 thread at a time. Therefore, we can only run 4 threads at a time. With this many threads, they are competing for the CPU in a way. So instead of speeding up the program, we are actually slowing it down. There is also some overhead with creating and destroying threads, and also context switching threads. So that slowdown might also be attributed to that. The time it takes for a CPU core to switch from one thread to another. That could also be what is slowing down our program. you're gonna repeat this same thing with 10 million threads, 100 million threads, and 1 billion threads. Once you have this whole table populated with speedups, we can then proceed to the final part, and that is to answer a few questions. Question 1. Where do you think the sweet spot was for the thread count? Do you think there was a thread count that consistently had the best results? And was there a point where you started to get worsening results? Actually, that part should actually be for question 4. So question 1 is, do you think there was a thread count that consistently had the best results? So with this example here, we can't say anything definitively because we haven't tried out the 10, 100, and 1 billion case yet. That is something for you to do. And you might get different results depending on your machine. Every machine is going to be a little bit different. So you might have a machine with more cores available than I do. In that case, you might get even more speed up available. So that's number 1. Number 2. Where do you think the sweet spot is for workload size? That is the number of terms. What was the smallest workload size that started to benefit from parallelism? So again, this is only answerable if we have the whole table populated. So at what point do we start to see a speedup is basically what I'm asking. Number 3. At what point do you stop seeing any speed improvements? And does this match up with the number of CPU cores on your system? Was there a point where you start to get worsening results? So, at least for the 1 million case, there was a point where I started to get worsening results, and it's at 16 threads, which is way over the 4 threads that I have on this system here. So, you might get varying results for 10, 100, and 1 billion terms, but again, this is something that you can only figure out once you have those values. Number 4. Okay, so that was actually question number 4. Number 3. Do you think this was a worthwhile speed up by the number of seconds saved compared to the first table? So if we look at the first table, we had runtimes on the order of a few milliseconds, and we were only able to save a fraction of a millisecond at best. 1 millisecond at best, if not a fraction of it. So it's at 8 threads that we it's at 16 threads that we stop getting any speedups at all, but it was also at around 8 threads that we get our best speedups. That speedup is only like 1 millisecond. So come to your own conclusion as to whether shaving 1 millisecond was worthwhile. But also compare that to a 1.29 times speedup. Yeah, so you're gonna compare absolute time saved versus actual speedup, and you're gonna determine whether this was a worthwhile speedup. So that's number 3. Number 5, only do this if you have a high core count CPU available. So something like the AMD Ryzen 9 or Intel Core i9, those are like the highest end desktop CPUs available. Those CPUs have core counts that are like 16 and more. So depending on your system, I guess this also depends on whether your system. This also depends on whether you are virtualizing your CPU onto a virtual machine, because as you've seen here, even though I have 16 CPUs here, I can only use 4 of them at a time, or at least I'm only using 4 at a time here. So, if you are able to run this program with even more threads, and your hardware can handle it, add an extra column and see how much more speed up you can get. Did you get a worthwhile? If you are able to run, if you are not on a system that has more than 16 CPU cores, did you get even more speed up? Okay, so that's something worth doing if you're able to do it. That's why it's optional. So 15 points per question except for question 5. And 30 points for the table, 30 points for the benchmarks. I'm not asking for any screenshots of the program running because that was already part of assignment number 2. So we're taking the program that we have written and benchmarking it to see whether we can get any appreciable speed up. If we can, was it a good speed up? Okay, so with that, these are the instructions for your Pthreads project. I plan to have it due, say, Saturday of next week. That gives you ample time to not only catch up with your second assignment, but also to give you time to actually benchmark your program. Okay, so that's gonna be everything for your benchmarking project. For OpenMP and MPI, you will have similar questions that you're going to answer, but you're also going to be answering the ease of programming as well. So when it comes to your Pthreads project, we don't have anything else to compare it to because we've only looked at Pthreads so far. When we get to OpenMP, I'll add an extra question saying, between Pthreads and OpenMP, which do you feel like is your favorite so far? So we're gonna benchmark a different program for OpenMP. Once again, it's gonna be a parallel program, and we're gonna see whether we can get any speed up. So part of the point of parallel programming is not only to leverage the multiple CPU cores on your computer, but also to see if we can get an appreciable speed up. And this program here, it's only scratching the surface of what we could be doing. So, with that, I'm gonna end the video here, and if you have any questions, I would encourage you to, talk to me over office hours. For 5250, you have an office hours. For the online section, you will have to schedule it with me, because it's totally async. But anyway, if you have any questions, let me know. We can schedule a meeting if you need to. Try this out, see how far you can go, populate the table, and we'll go from there. Okay? Alright, thank you.